Now we're going to talk about symmetry, when a graph has symmetry. With respect to the x-axis, if I recall, here's my x-axis right here. And it's symmetric as if, imagine if I folded this paper on this dotted line right here. If you fold it there, then you can see that the graph matches the same that it would be if I folded it here. And that means it's symmetric about the x-axis. Now, algebraically, to test for this, we will plug y in, negative y in for y, and then solve it. And we're going to do this in just a minute. For y-axis symmetry, that's checking to see if our graph has symmetry with respect to our y-axis, which is here. So if I folded my paper in half long ways, you can see that these two would fall right on top of each other. Algebraically, we're going to replace negative x with x and calculate. And then for origin symmetry, we have it's symmetric about the origin, so it's basically if I folded it in half and then folded it long ways, they would land on top of each other. So x is replaced by negative x, and then we replace y with negative y. That negative jumped up there, it's off a little bit, but it's replaced with negative y, and we test for origin symmetry. So let's look at an algebraic example. Let's go ahead and see these things. We want to know if our y equals x squared plus 4 is symmetric about the x-axis or the y-axis. So the first thing I'm going to test for is I'm going to say, well, does this thing have y-axis symmetry? Question mark. So we take our original function that was given to us, and we want to evaluate it at negative y, meaning everywhere there is y, replace it with negative y, and then simplify. There's nothing else that can be simplified about this, so I compared this to the original. They're not exactly the same, therefore this does not have symmetry. So it's not symmetrical about the x-axis. So I would say no. No y-axis symmetry. No x-axis symmetry, excuse me. Let's check for y-axis symmetry. If you look back in our table, we say, well, is this symmetric about the y-axis? Take your original function, and this time we're going to plug in negative everywhere there's an x and simplify. Well, this can be simplified. A negative x times a negative x, because it's squared, is going to be a positive x, which just gives us positive x squared plus 4. So when I compared this to the original, it's exactly the same. This is going to be symmetric, so I would say yes, this is symmetric about the y-axis. Now origin, we don't necessarily have to do a whole nother step for origin. Origin says replace the negative x and replace with negative y, and they need to be exactly the same. This one's not symmetric, therefore it can't be origin, because origin means it's symmetric about the x-axis and the y-axis. They both have to be symmetric for you to have origin symmetry. The next thing we're going to look at is even and odd functions. A function is an even function if when you evaluate it at negative x, you get the original function for all x in the domain. Basically, it's also y-axis symmetry. Okay. When we have an odd function, if we take negative x, we evaluate our function at negative x, and we get the complete opposite of the original function for all x in the domain, we will have an origin symmetry. Okay, so that's kind of, we're going to look at even and odd, and they're going to tell us about our symmetry as well. So first of all, determine whether each function is defined even, odd, or neither. Anytime we are asked to find even, odd, or neither, we are always going to evaluate our function at negative x. So we want to put evaluate your original function at negative x. That means everywhere in my problem that I have an x, I put a parenthesis and then I go back and substitute negative x there. And then we're going to calculate. Negative x, that's negative 1 times negative 1 times negative 1 is a negative. So negative x to the third power is negative x cubed, and then times a negative. And then right here we get negative x times 2 is negative 2x. We're still simplifying. When you have a negative times a negative, you're going to get a positive x cubed minus 2x. So when I compare my resulting to my original, this negative x cubed is exactly opposite because one's positive, the other one's negative. And then my second term is plus 2x. It's exactly opposite. So this fits the case of our odd function because the resulting solution is exactly opposite the original, and that's what that means. So term for term for term. So if I had 10 terms in my original polynomial, my original function, I would have to test each term, and it would have to qualify as the exact opposite every time. Alright, we want to know even, odd, or neither, so we know our method for that is to evaluate at negative x. So everywhere there's an x, I'm going to put a parenthesis, and then go back and substitute all my x's with negative x. And we're going to evaluate. So a negative number to the fourth power is just going to be positive x to the fourth, 2. A negative x, which is like a negative 1x squared, is just going to give me x squared, and then I have that negative 2 out front, plus 4. So then this gives me 2x to the fourth minus 2x squared plus 4. Compare the result to the original, and it's term for term for term exactly the same. So therefore we have even. And even means that it's going to have a y-axis symmetry. And let's finish with our last one, which is C. It's g of x. We're always going to evaluate this thing at negative x. I'll put parentheses everywhere there's an x, and then I substitute negative x in there, and then simplify. A negative 1x to the third power is just negative x cubed. A negative times a negative is a positive x plus 7. So let's test this thing. X cubed, negative x cubed, opposite. Negative x, positive x, opposite. But then this one's exactly the same. So this whole function is not exactly the same, nor is it exactly opposite term for term for term. So this is one in which it is neither.